What's up, guys? Today we're going to be solving this problem. We're given that an insurance company sold 300 fire insurance policies with these different values. They had two different policies, one that had 200 individuals with a policy maximum of 600 and a probability of claims for policy of 0.04. The other had 100 individuals covered, a policy maximum of 300, and a probability of claims per policy of 0.03. We're given that the claim amount for each policy is uniformly distributed between 0 and the policy maximum. The probability of more than one claim per policy is 0, and claim occurrences are independent. We're going to be using the normal approximation to calculate the probability that aggregate losses are greater than 5,000. So the first thing we can do is call this policy A and this policy B. Then we can say that S, our total aggregate losses, is equal to the aggregate losses of policy A plus the aggregate losses of policy B. Then, from the individual risk model, we have the expected value of our total aggregate losses is equal to the sum of the individual expected values of each different policy. And similarly, we have that the standard deviation of S is the square root of the sum of those variances. And the reason we're using the standard deviation is since we're going to be using the normal approximation, it'll lend itself a little bit easier to what we'll be doing in a little bit. So then, let's start thinking about these individual distributions. So we can define the sum of aggregate losses under policy A as follows. The sum between I equals 1 and NA of all the XI's that come from the loss distribution A. So this is the frequency of loss A, of policy A, of losses under policy A, and this is the severity of losses under policy A, of an individual loss. Then, we can define that the number of losses is actually binomial, with M equal to 200 and Q equal to 0.04. How did we do that? Because there's no probability that a claim is more than one per person. The probability of more than one claim per policy is 0. So in other words, we have either 0 or 1, and so we're summing up 200 independent Bernoulli trials with probability of success Q, and all of them are independent. That means that our frequency follows this binomial. Similarly, we're given that the severity follows a uniform distribution between 0 and the policy maximum of 600. We can do something similar for S sub B, and for similar reasons, we have the frequency of under policy B is another binomial, this time with 100 and 0.03 as the parameters. And similarly, losses under policy severity of losses under policy B are uniformly distributed between 0 and 300. Again, that's what's given as our policy maximum. So with that, since we're defining this under the collective risk model, we can go ahead and use what we have for that, which is that the expected value of S sub A is just the expected value of the frequency of A times the expected severity of A, which we can take the expected value of a binomial is just 200 times 0.04, and the expected value of a uniform from 0 to 600 is just the midpoint there, which is 300. And that comes out to 2,400. We can do the same thing for policy B. That one comes out to 100 times 0.03 times this midpoint of 150. And that comes out to 450. Now for the variances, we're going to use our formula that tells us the variance is the expected value of the frequency times the variance of severity plus variance of frequency times expected value of severity squared. And again, we have the expected value of the frequency is 200 times 0.04, and the variance of this uniform, 600 squared over 12. And for the next term, the variance of a binomial is this times 1 minus this, which in our case is 200 times 0.04 times 1 minus 0.04. And then, of course, times the expected value of our uniform, which we previously said was 300. And that is going to come out to 931,200. And finally, for similar reasons, the variance of B comes out to the expected value of this binomial, 100 times 0.03, times the variance of that uniform, which is now 300 squared over 12. Similarly, plus the variance of this n, which is again m times q times 1 minus q, or 100 times 0.03 times 1 minus 0.03, times the expected value of that uniform, which we said was 300. Sorry, we said was 150. And of course, we have to square both of those. I had forgotten to write that over here, so that's a very clear mistake that can be very easy to make, as you just saw. So this one comes out to 87,975. So now we can fill in the information up here with what we've already found. So we add up the expected values, 2,400 plus 450 equal to 2,850. And the square root of the sum of the variances, I'll skip writing that out for you. Adding up these two numbers comes out to 1,019,175. And now we have all we need, oops, wrong button, sorry. We have all we need to use the normal approximation to compute the desired probability. Probability that S is greater than 5,000, where S is the total aggregate loss under both policies, we know is equal to 1 minus the complement, which is S less than or equal to 5,000, and by the normal approx, we have that that's approximately equal to 1 minus the normal CDF of 5,000 minus the mean of S divided by the standard deviation of S, which we already found on the previous page to be 5,000 minus 2,850 over root 1,019,175. And I'll simplify that down for us, and we get that that's approximately equal to 1 minus the normal CDF at 2.13. From our tables, that comes out to 1 minus 0.9834, which is equal to 0.0166, which is the answer that was given in class. So to summarize everything that we did, we defined the total aggregate losses as the sum of the individual aggregate losses under each policy. We're thinking of kind of these losses as individuals under the individual risk model. Then we worked backwards and found the distribution of each of those individual aggregate losses using their frequency and severity. We used the rules that we've established there to compute their expected value and variance. Then we put that into the individual risk model rules to compute the expected value and standard deviation of our aggregate S. Then finally, we used the normal approximation to compute the probability that total claims between the two policies exceed 5,000, and we arrived at the answer given in class. And as is customary, I'm going to draw one of the couple of cartoons I know how to draw, which in this case is an angry face. But we're not angry, we're very happy because we just did some math. Hope you all have a wonderful day.